Hello there, researchers and electrical engineering community and stakeholders. This is Carlos Leal and Nelson Florez. The electrical engineering and energy industries are constantly facing different challenges, including the protection of distribution lines when impacted by indirect lightning strikes. This natural phenomenon can cause failures that represent expense and resource losses. Evaluating the indirect lighting performance of distribution networks becomes important when designing all network protections. Different methodologies have been proposed for the calculation of lighting-induced overvoltages, like the Monte Carlo method, the use of the Heuristic formula, and all the other presented in the latest IEEE standard 1410-2010. However, accurate results are mostly obtained with a high number of simulated events, so calculating lighting-induced overvoltages and flashover rates requires great computational effort. Several heuristic techniques have been proposed to reduce the computational cost of these evaluations, including the ones proposed by Borghetti, Nucci, Mestriner, Soto, Napolitano, and the others. There are three main goals with this study. The comparison between the three different techniques will provide important results, since for any industry the reduction of resource cost is always relevant, and this result will allow us to determine the best and most reliable tools and techniques for complex and specific scenarios.
It's very important to mention that the adopted method to calculate indirect lighting performances on distribution lines is the one proposed by the IEEE standard 1410-2010. A lighting incidence model and an electrogeometric method are used to discard direct strikes, leaving only indirect strikes for further calculations. Yallour's draw software allows to simulate all generated events within the striking area A, and to calculate the lighting-induced voltages following the procedure mentioned before. Also using the Agrawal coupling model that includes the effect of soil resistivity and the ATP transient program. When all the simulations are calculated, the flashover rate is estimated with this equation. Presents a graphic approach to evaluate different lighting parameters compared with all previously calculated events. This evaluation consists on the following conditions. If the current event complies with all these conditions, it's not calculated by the technique. This technique presents a least squares fit to follow the dependence of the presented regression model. Is a proposed approach to the Heuristic formula described in two stages. The first stage uses this formula to limit the domain of the strike locations generated by the Monte Carlo method, and to determine the dependence between each calculated lighting-induced voltage and the different variables that are part of the following equation. The second stage is to use the Yallour's draw software to calculate only the events that surpass a minimal critical voltage. It's also important to consider two different features. First, the percentage of discarded events against the total number of simulations from the base case, that we will call in this project PDE. And also the mean error between the flashover curves obtained by the three techniques against the reference curves obtained in the base case.
The design of the base case is defined in accordance to the regulations for minimum voltage network installations proposed in the ASTM B232 manufacturing standard. The chosen ACSR line is a Raven model, one AWG gauge, one Class A zinc-coated steel cord, and 6 1350 H19 aluminum wires concentrically wired. The design will also have poles placed every 100 meters and fixed value resistors with the same value of the characteristic impedance, 497.3 ohms, added to each end of the line to avoid reflections. The chosen test cases are three. We also choose 3 typical ground conductivities. It's also important to select appropriate striking areas depending on the symmetry of the test cases. The MTLE model is chosen with a 2000 meter attenuation constant. We also assume a return stroke speed of 120 meters per microsecond, and a channel-based current is set to be a double Hydrold function. For the purpose of this project, it's important to highlight that all the Borghetti et al. Results were obtained with an R sub k equal to 400 meters. For the multi-nonlinear regression technique, the site L and N sub f will have the following selected values. And finally, note that the minimum insulation level and critical overvoltage are both 50 kilovolts for all techniques.
These are the figures and tables obtained with all heuristic techniques. The tables show the percentage of discarded events and the mean error obtained by every heuristic technique on each network topology for each ground conductivity. The following is a demonstration of the Rusk formula technique implemented in MATLAB code for a straight line with infinite ground conductivity. We can see the flashover rates results obtained by Jaloux draw that are considered the reference values, and also the flashover rate obtained by means of the heuristic technique. The code also presents the amount of discarded events and the obtained mean error of the heuristic technique in question. The Rusk formula technique allows discarding the highest amount of simulated events for finite conductivities on any network topology, and it is also the most reliable technique, reaching a mean error value of 0 on all infinite soil conductivity test cases. The Borghetti et al. Heuristic technique presents the lowest percentage of discarded events for any network topology, but it still achieves a significant reduction above 74.09%. Also, note that the multi-nonlinear regression technique is the second most accurate technique found after the Rusk formula heuristic.
In conclusion, the implementation of the Borghetti et al. Technique allows a reduction between 74.3% to 85% on the straight line test case, and up to 84.4% and 87.5% on the T-shape and H-shape test cases, respectively. It also achieves lower mean error values than the multi-nonlinear regression technique. The multi-nonlinear regression technique shows a reduction between 92.7 and 93.9% on a straight line case, while achieving a reduction of up to 92.3 and 97.5% on the T-shape and H-shape test cases, respectively. This technique can be considered the most effective in reducing computational cost, but the least accurate among the others. The Rusk formula technique eliminates up to 94% of the total number of simulated strikes in a straight line test case, and up to 94.7 and 94.3% in the T-shape and H-shape, respectively, test cases, obtaining the second highest percentage of discarded events for all topologies and ground conductivities. What makes Rusk's formula the most reliable technique is that it greatly reduces computational cost while providing the most accurate flashover rate compared to the other techniques, reaching total accuracy for infinite ground conductivity and reaching error values as low as 1.7% for at 0.01 Siemens per meter conductivity, and error values lower than 10% for at 0.001 Siemens per meter conductivity. We hope our implementations and analysis provide a helpful landscape for the purpose of your investigations and interest. Thank you for watching. At Leal, we wish you a great day.